Infinite Possibilities Conversion. In Part 1, Quantum Think series, we explored the unsettling idea that the universe runs on probability, not certainty. Now, as thunder rumbles in the distance, we reconvene to push that idea further. How can we engineer outcomes in a quantum world ruled by chance? Joseph, last time you left me with a thought that's been nibbling at my mind. You cannot control events, but you can shape probabilities. In other words, quantum reality goes from possibility to probability to event. And what we call certainty is just an emergent illusion from lots of random events averaging out. It was a lot to take in. Now I have to ask, if we can't control things at the quantum level, how do we ever get anything done? How do we go from understanding this bizarre probabilistic reality to actually engineering something useful out of it?
That's the golden question, isn't it? Indeed, on the quantum stage, we give up on absolute control. But giving up control doesn't mean we're powerless. Instead, we become choreographers of possibility. Think of it this way. We can't script the exact dance of every quantum particle, but we can design the stage and the music so that the dance is likely to end in a pattern we want. In quantum terms, we set up conditions that bias how things will happen, nudging nature's own randomness toward favorable outcomes.
Bias how things will happen? You mean like loaded dice? We load the quantum dice so they roll our way.
Exactly. We can't rig a single quantum toss to always land the way we want. Nature won't allow a fixed outcome. But we can weight the odds. It's like loading the dice in our favor. We shape the probability landscape of events so that when a random quantum roll finally occurs, it most likely yields the result we desire. We engineer by design, not by control.
In Part 1, you described how a simple light bulb is actually a testament to quantum probability. An excited electron in an atom will randomly emit a photon. We never know exactly when. If even something as ordinary as a light bulb harbors this randomness, how do engineers deal with that? Or do they just live with the uncertainty?
Great memory. The light bulb analogy really shows how deeply randomness is woven into reality. But here's the key. While we can't predict or command the exact moment an excited electron drops and emits a photon, we can influence the odds around it. Think of an excited atom like a tiny ticking time bomb set by quantum rules. It might go off in nanoseconds or linger longer. We can't say, explode now, but we can design the environment to gently encourage it.
How so?
For instance, by surrounding the atom with particular materials or placing it in an optical cavity, imagine mirrors trapping light around it, we can change the probability of emission. It's a bit like nudging that atom's mood. Maybe we make it more impatient to emit or channel its photon in a particular direction. Engineers do this in practice. In specialized light sources, or LEDs, they choose materials and structures that shorten the excited state's lifetime, or funnel the photon along a desired path. We're shaping the photon's fate statistically. We can't force a single atom's hand, but with millions of atoms, these tweaks add up to reliable light.
So even though each atom acts like a random prima donna, by designing the stage, you get an almost steady performance out of the ensemble. It reminds me of how 1 trillion radioactive atoms together have a precise half-life, even though one atom decays unpredictably. Certainty from numbers.
Exactly. Certainty as an emergent property. One atom is unpredictable, but en masse, the law of large numbers gives us predictability. We leverage that in engineering all the time. But quantum engineering goes a step further. Not just relying on large numbers to average things out, but actively biasing the chances before we have large numbers. We prepare single systems in clever ways so that when measured, they're likely to give a useful answer even on the first try.
That sounds almost like trickery. like you're asking the universe a question and somehow rigging it so the answer comes out in your favor. Is that how quantum computers work?
That is exactly how quantum computers work. We don't get around the fundamental randomness, we ride it. A quantum computer sets up a kind of interference experiment that sculpts probability amplitudes. The computation is not a step-by-step deterministic calculation like in a classical computer. Instead, it's more like designing a wave interference pattern. The peaks of the waves represent high probabilities for certain outcomes, and the valleys represent low probabilities for others. By the end, the correct answer should lie under a peak, high probability, while wrong answers are in the troughs, low probability. Then nature does its random thing. We measure, basically rolling the quantum dice, but because we've loaded those dice, we most likely get the right answer.
This is mind-bending. So, rather than crunching through every possibility logically, a quantum computer uses physics to navigate the possibilities, like a kind of guided randomness.
Nicely put. It's guided randomness. We allow all possibilities to unfold at once, then guide them using interference. Perhaps an analogy will help. Imagine you're searching for a specific item in a vast, pitch-dark warehouse filled with boxes. A classical computer would have to stumble in the dark, checking boxes one by one with a flashlight. A slow, plodding certainty that eventually you'd find what you seek. But a quantum computer is more like flooding the warehouse with ripples or waves that touch all the boxes simultaneously. Most of those waves cancel each other out in a mess of destructive interference, but you set it up so that, at the location of the prize box, the waves constructively interfere, reinforcing each other. After this wave passes through, you briefly shine a light, and lo and behold, the area around the prize is glowing brighter than anywhere else. You've effectively made the right box far more likely to be the one lit up when you look.
That's a fantastic image. The prize box glowing in a dark warehouse because of interfering waves. So the quantum algorithm is like an interference trick that makes the answer stand out. Can you walk me through a real example of this? Say, how would an actual quantum algorithm do this wave interference guiding in practice?
Let's talk about Grover's search algorithm, a famous example of exactly that. Grover's algorithm is a quantum routine designed to find one marked item out of an unstructured list, like Not Sorted or our box in a warehouse. Classically, if you have n possibilities, you check approximately n over 2 on average before you find what you want. In the worst case, n checks. Grover's algorithm can find it in roughly square root of n steps. For example, if n were 1 million, you'd need on the order of only 1,000 steps instead of 1,000,000, a dramatic speed up. Here's how it works in concept. Superposition, exploring all options at once. First, the quantum computer prepares a superposition of all n possibilities. In our warehouse picture, this is like spreading a very faint equal glow to every single box, as if you're considering all boxes simultaneously. Every possible state gets an equal amplitude to start with. Marking the target, the oracle's phase flip. Next, the algorithm uses a quantum subroutine, often called an oracle, that can recognize the correct solution if it sees it. When applied, this oracle doesn't tell us the answer outright. That would collapse the state. But it does something clever. It flips the phase of the quantum state corresponding to the correct item. In the warehouse analogy, think of it like giving the correct box a special tag that says, "You're different." Not brighter yet, just a subtle tag. In terms of waves, the wave touching the target box is shifted out of phase, like inverting it, turning a crest into a trough. We now have an interference condition set up. The marked state is just a little out of step with the others. Interference, amplifying the marked state. Now comes the heart of Grover's trick. We apply a diffusion or amplitude amplification step. This is essentially a gentle quantum feedback that takes the average amplitude and inverts all amplitudes about that average. What does that mean? Imagine all those probability waves and how we gave one state a phase flip. This step causes those waves to interfere. The effect is that the amplitude, the brightness of the marked state increases, while all the other states' amplitudes decrease slightly. In our warehouse, it's as if that tagged box now starts to glow a bit brighter and the rest dim down a touch. The correct answer is being singled out, but only by a small amount in one round. Iteration. Repeat to sculpt the probability landscape. Grover's algorithm then repeats the phase marking and interference amplification multiple times. Each cycle makes the target state's amplitude bigger and the others smaller. It's like pushing a swing. Each push gets the amplitude of the desired state higher and higher. If you do roughly square root of n iterations, the target state becomes overwhelmingly likely to be observed. The warehouse now has one box shining clearly brighter than all the others. Measurement. Reading the outcome. Finally, you look. You measure the quantum state. This is the equivalent of opening one box to see what's inside. Because of all the prior interference magic, the odds are heavily in favor that the box you open is the special one, the glowing box with the prize. In quantum terms, when we measure, we collapse the system into one definite state. And thanks to our engineered probability bias, that state is, with high probability.
And thanks to our engineered probability bias, that state is, with high probability, the marked solution we were looking for.
And that's how the answer appears. Not by brute force checking every possibility, but by sculpting the probability so the right answer is almost inevitable when you finally check. It really is like loading the dice.
Absolutely. The algorithm didn't calculate which item was special in the way a classical program would. It orchestrated a kind of dance of quantum states, where only the special state gets to hog the spotlight. We bias the quantum odds so heavily that when randomness finally plays its hand, it delivers us the prize.
How confident can we be in the result? You said with high probability a few times. Is it ever wrong?
Good point. There's always some residual chance of failure, because we never eliminate randomness entirely. If we stopped a bit too early or too late in Grover's iterations, the target might not have maximum probability, and we could miss it on the first measurement. But the beauty is, even if you don't get it the first time, you can rerun the algorithm a few times. The odds are so stacked that you'd very likely succeed in one or a small number of tries. And if tuned just right, one try does it. In essence, quantum algorithms give us advantage, not perfection. They turn a painfully long search into something feasible by amplifying the right answer's chances dramatically.
It feels less like computing, more like finessing nature. Instead of brute force, you're coaxing the answer out of the universe.
I like the way you put that. We're coaxing nature. Indeed, quantum computing is as much about asking properly as it is about answering. You ask the universe your question by setting up an elaborate experiment, the quantum circuit. And if you've done it right, the universe answers when you measure, with a random outcome that is, more often than not, the one you wanted. It's a fundamentally different paradigm from classical computing, which is all logical certainty within its digital rules. Here, we embrace uncertainty and tame it.
It's a paradigm shift for sure. Classical thinking asks, what will happen? Quantum thinking asks, what can happen, and how likely is each possibility? That shift in mindset, I can see how it makes one a better scientist or engineer. You stop trying to force outcomes and start designing conditions.
Precisely. When you realize certainty isn't fundamental, you stop wasting energy on trying to guarantee a particular outcome from one isolated event. Instead, you design the odds in your favor across many events or in a holistic system. That's how we build reliable technology on unreliable quantum events. A laser, for example, gets billions of atoms to collectively emit an intense beam of light by creating just the right conditions, population inversion, and an optical cavity, so that random emissions trigger more emissions in a chain reaction. The randomness of each photon emission is harnessed into a useful, coherent process. In quantum computing algorithms, we carefully design the circuit, a sequence of quantum gates, so that through phenomena like superposition, interference, and entanglement, the probability of the correct answer is amplified.
You mentioned entanglement there. We haven't talked about that yet, but it's one of the famous quantum weirdnesses. Does entanglement play a role in engineering outcomes too?
It does, especially in more complex algorithms. Entanglement is like a coupling between quantum objects. Their fates become intertwined. If you entangle two particles, you can't describe one without the other, even if they're far apart. In our engineering analogy, entanglement is like pairing up dancers so that they move in sync. If one dancer makes a move, the partner mirrors it instantaneously, no matter the distance. This can be useful. By entangling qubits, quantum algorithms can enforce relationships between pieces of information. It's another tool for shaping the probability landscape, ensuring that only outcomes that satisfy certain correlations, like two bits being consistent with each other or fulfilling a constraint, get amplified. In short, entanglement lets us design more intricate probability patterns, linking parts of the system together.
So superposition lets you explore possibilities. Interference lets you amplify the right ones. Entanglement lets you tie pieces together. And iteration lets you amplify successively. And at the end, you measure, which is like asking nature to pick the final answer from the weighted options.
Well summarized. Each of those is a pillar of quantum engineering. Superposition, create all possible paths. Entanglement, connect parts so their outcomes are correlated as needed. Quantum gates, operations. These are our design tools. They rotate, flip, and tweak the probability amplitudes, introducing phases and correlations. Interference, the result of those operations. Some paths reinforce, others cancel, sculpting the probability distribution. Iteration, repeat certain operations to amplify the desired outcome more and more. Measurement, the final readout, where the quantum possibilities boil down to one reality. In the end, we're not calculating the answer step by step. We are shaping the likelihood of each answer, and then letting the universe's own randomness collapse the state to give one outcome. If we've done our job right, that outcome is the answer we wanted with very high probability.
It's like solving a maze by flooding it with water and letting the currents carry you to the exit, rather than walking every corridor. You set it up and let physics do the heavy lifting.
I love that analogy. We set up the maze, the problem, in water, the quantum state, with currents, interference patterns, that naturally flow toward the exit, the solution. The water might not take the exact same path every time, but it overwhelmingly ends up at the exit.
This has been illuminating and quite dramatic in the best way. We started with the seemingly unsettling idea that the universe is playing dice at the smallest scales. Now I see it from a new angle. If you can't stop the dice, load them. Quantum advantage isn't about brute forcing faster, it's about biasing the odds. We embrace the uncertainty and then craft it to work for us.
Well said. The power of quantum thinking is in accepting the fundamental randomness, but not throwing up our hands. Instead, we find clever ways to make randomness yield useful results. We bias the outcomes and then let nature take its course. In essence, we collaborate with chance.